Photoelectric effect. We have a metal here, and that has got lots of free electrons, a metal. And we send a wave, a light, or any electromagnetic wave with a frequency F1. And say lambda 1 is the wavelength, and with a intensity I1. And we send another wave with F2 lambda 2 and the same intensity I1. And then we send another wave. We're getting the metal exposed to this light, or we shine this light, or get the metal having contact with this electromagnetic wave with this frequency and the wavelength. So F2, this is F3, lambda 3, and the same intensity I1. So F1 is less than F2 is less than F3. That means that the green one has a high frequency wave, and F2 is in the middle, and F1 is the smallest one. And the intensity is the same. So what's happening? The first wave, the red one, when we shine that light, nothing happened. Nothing happened to the electrons. But when we shine that blue light, those electrons, like say 2 or 3 electrons, were emitted. So they were expelled from the metal. And now when we send a green light, which is the high frequency, but the same intensity, we got the same number of electrons emitted, but they have got kinetic energy. They have got lots of energy compared to the blue one. So the intensity is the same, but the frequency is increasing. With red, nothing happened. With blue, we got 2 electrons emitted. And with green, we got the electrons emitted, and they have got lots of kinetic energy in it. So now we are going to do the same to the same metal again. So we got the red and blue and green. I'm just putting in different colors just to say they are in different frequencies. It's nothing to do with the blue wave or green wave or green. So it's about they all have different frequencies and different wavelengths. And now this one has got F1, lambda 1, but intensity is I2 with more intensity. And this one we have got F2, same frequency, which means same wavelength, but the intensity is I2. And green one here, F3, lambda 3, and I2. So I2 is greater than I1. So that means that we are applying the wave or getting the metal exposed to that light with high intensity. So intensity is increased. That means more power, but the frequency is the same. So what's happening now? So just like above, that with the red one, we didn't have any electrons emitted from here. So same thing happened here. Although we increase the intensity to I2, which is greater than I1, nothing happened. And for the next one, the blue one, instead of 2 electrons, we got 4 electrons got emitted. So we increase the intensity, but the frequency is still F2. And for the last one, we got 4 electrons emitted, but with the same energy. So here is also Ke, and that also Ke. So the kinetic energy is the same for both green ones. And for the blue ones, they just got emitted, but more electrons. So more intensity means more electrons, but the kinetic energy is the same. So how do we explain what we have observed? Einstein said that these waves, the light waves or electromagnetic waves, and he said that although they are waves, they carry the energy in packets. So in terms of energy, they carry these discrete packets, and these packets will carry some energy. And he also said that when we shine this light to say this is a metal, and when we shine light, and we're actually sending these energy packets, and those energy packets will interact with electrons here. Okay, so the energy carried by these waves, they depend on the frequency of the wave. So that E is actually proportional to the F, which is a frequency. And that will be given by E is equal to HF. So E is equal to HF. And this is quite an important equation to find energy from a frequency by multiplying a constant called Planck's constant. So that's Planck's constant. That's really an important equation. So the energy carried by photons is given by HF. So what we have here is we have electrons here, and it's exposed to this light wave which consists of photons. If the energy carried by the photon is sufficient to get the electrons out, that means the electrons will be emitted. But if it's not enough, electrons won't be emitted. And if it's more energy, that means the electrons will be emitted, that will have lots of kinetic energy. So how do we know how much energy we need to emit those electrons, and how do they interact? So these electrons have got this interesting property that the photons will be absorbed by the electrons to get out of this place only if that energy is bigger than the energy required, right? So if you send a wave with a low frequency, according to this equation, it's not carrying lots of energy, right? So here the red one is the frequency is less than the other ones. So if the photons have less energy, that means less frequency, the photons would say that's not enough for me to get out. And if the photons have a higher frequency, that means more energy. So that means the electrons will absorb that photon and get out. And if the frequency go higher and higher, what would happen is that they will get out with really big kinetic energy. And if you increase the intensity of these photons with the same frequency, high frequency, that means you will have more photons interacting with these electrons. And other interesting point is that one photon will interact only with one electron. So this one will help this one to get out, and this one will help this one to get out. So one by one, and that's the way it works. That's the reason that for the same frequency, if we increase the intensity, we will have more photons. That means more electrons will be emitted. But they all will have the same kinetic energy. That means the energy depends only on the frequency. The minimum frequency of the photons that we need to get these electrons just out of that metal is called threshold frequency. So we can apply a frequency above that. That means that the electrons will have more energy. But with F naught, we can get them out. And so the energy required to get them out of the metal is given by work function, which is phi. So we can actually write that phi is the the minimum energy required to get the electrons or get the electrons emitted is given by using the same equation HF naught. So if we apply a photon, so wave with a frequency f, that means we are going to apply the energy HF. So that HF will be enough to get the electrons out and also to have some kinetic energy, right? So we can actually write that HF is actually equal to HF0, which is the frequency required to get the electrons just out, and plus the kinetic energy. So that's given by maximum kinetic energy, the Ke. So we can write down that HKE is actually HF minus HF0. So HF0 is the function we talked about, phi, work function. So we can say Ke is equal to HF minus phi. And it's a very important equation in photoelectric effect.